So I was saying that in this particular case, there is still unsymmetrical filling of the d electrons into the different directions. Like x, y, z, it is not symmetrically filled with your d electrons. That's why, because of the unsymmetry, we have the electric field gradient and there would be delta EQ. That won't be zero. So is this point clear? Because earlier we were talking about the states which are having at least same energy. Here the energies are also not same. When that splitting has happened, we can't consider just that whether it is paired or not. So you need to see how much electron density is in the x direction, y direction, and z direction. Since you will see that energy levels are not same and that is unsymmetrically filled, so that would be a case where EFG will exist and therefore delta EQ will exist. Is this clear?
Okay, ma'am. Clear.
Yeah. So now there is okay. So actually we have a trend. So we need to understand if we have iron CP2, iron CP and CP star, and we have iron CP star whole twice. So the MOSFET spectra observation says delta value is 0.53. This is also around 0.50. This is 0.49. And the delta EQ value is 2.39. This is 2.44 and this is 2.47. So you can see the delta value is decreasing, whereas delta isomeric shift value is decreasing and photopole splitting is increasing. Why is it happening? Firstly, in case of iron CP2, we saw that iron is in +2 oxidation state and certain delta value is there, and delta EQ is existing because lattice contribution or valence contribution is existing. It is not symmetrical in nature because we are considering the staggered nature. So in staggered one, so there is no proper symmetry, so there would be electric field gradient and we have certain value. Now what about the CP star then? In CP star, here also we say that iron in +2. And then why the delta value, that isomeric shift value has decreased? If you will consider the delta value is going towards more negative side. If it is less value, that means it is more negative compared to that. Now, generally, if we have CP with a methyl version, which is a CP star, you know that methyl has a tendency of plus I effect. That's a inductive effect. It will give the electrons through inductive effect, which is not a permanent effect. So when it is giving the electrons through inductive effect, it is increasing the electron charge density on the CP ligand. So this is increasing. So when this is increasing, since it is maintaining the overall charge, iron +2 starts going to iron +2. That means the loss of one side, it is having more electron density, and the other side, the electron density is removing. So has to have a balance because it is maintaining its +2, like overall charge is maintained. So here, it will not show you exactly like +3 has been become, but there would be movement or shifting of the d electrons. So that happens. Because of that reason only, we see more negative value in case of iron CP and CP star when one has been replaced. In case of iron CP star, where both the CPs have been replaced by the CP star, so now you can consider earlier it was just one ring. Now both the rings are CP star. So too much of electron density. So because of that negative charge electron density, it has to be balanced. For balancing, if one side it is having more negative, other side has to become positive to have a overall balanced charge. So it would be having more shifting of d electrons. That means more loss of d electrons from the iron. That's why it goes to even more delta negative. So is that clear or should I repeat it one more time?
Okay, ma'am. Once again, explain FeCP star 2 complex.
Okay. So earlier we have iron CP. So we generally say, if I would take this example, I have a ligand which is giving more electrons to my metal center. If more electrons is coming to metal center, so that means it should increase the d electron density. That is what we were having. That weak field ligands would be giving more electron density to your metal. Therefore, there would be less delta value, negative, right? But in this particular case, what we generally have, since these CP ligands, these CP and CP star ligands, they are redox non-innocent ligands. There are two categories of ligands, except besides that strong and weak. One is innocent and other is non-innocent. Innocent means which does not participate in any kind of redox properties. Redox property says oxidation and reduction. That means it will not lose the electrons, it will not gain the electrons. That is called as innocence. But if it is not innocent, that means it will participate in gaining the electrons or losing the electrons. That is where, when I have changed the CP to CP star, it has a tendency to gain more electron density, because methyls are having plus I effect, and that will increase electron density. Now, what we will expect? If ligand is having more electron density, so it will give more to the iron metal. If that is a scenario, delta value should have been decreased. Delta value should have been like less negative, because d electrons would be more, and when d electrons are more shielding will happen. So the delta value has to be less negative. But what we are observing in case of CP star, since it is a non-innocent ligand, redox non-innocent ligand, so what it will do, it will have more charge density, and to balance it out, iron starts losing the electrons, d electrons. So when this happens, it moves towards iron in plus 3. So whenever we have iron in plus 3, it will give you more delta negative. That's why in case of iron CP, CP star, it goes towards 0.53 to 0.50. When we have both the CP or CP stars, that means more negative is coming from ligand. To balance it out, now iron would be more oxidized, therefore the delta value becomes more negative. So now is this clear?
Clear, ma'am.
So the delta value, I know this is a bit tricky to understand. As I said, in calculating the delta value or in understanding the isomeric shift, we just cannot jump to the having the basic concept of methyl will give more electrons, so it should be having the reverse trend. We should not think about that. Every single complex is having different behavior and different. We need to use some logics to get to know the answers. Now coming to the delta EQ, the splitting value. So the splitting value, we already know that it comes from the lattice and valence contribution. So the question is, why splitting value is increasing when we go from iron CP2 to CP CP star and then CP CP star, like both of them is there. First reason is clear, from CP2 to CP CP star, because there are two different kinds of ligand. One is having methyl, other is not having methyl. That's why more delta EQ is happening, because contribution is more, unsymmetry is more. But why in case of iron CP star to CP star 2, it is happening more? Because here when we have more electron density coming from the ligand, that more movement starts coming from the iron. So when there is more unsymmetry in the iron d orbitals, it will lead to have more delta EQ value. So that is why we have more delta EQ for the iron CP star. So is this clear?
Clear, ma'am.
Okay. Now we will take up, I don't know how much we take. It's 37. Okay. So there is one more thing. When we have iron CP, this is iron 2. If it loses its electron, it becomes if it loses its electrons, it becomes ferrocenium ion. where your iron is in +3. So here iron is in +2. So this case is very tricky. So you need to analyze this concept very properly. So when we check the MOSFET spectra, we get to know that delta value here is 0.53. Here also it is 0.53. And the quadruple splitting, delta EQ, it's 2.39 here, but 0.1, that means negligible in this particular case. Now, generally, all the concepts, what we have understood, if I have iron 2 and iron 3, which one is going to give me more negative value?
3, Fe+3.
So why in this particular case, when we have iron in 3 state, still the delta value, that isomeric shift is still the same. So graph looks like this way. Here, if we have first, and for this ferrocenium, it is just one peak coming like here. So both of them, they come at same delta value. So the reason behind here is, as I said, these CPs are redox non-innocent ligands. So what they does, even if iron is in +3, so they start balancing out the charge and electron density start coming from your CP. Therefore, it balances out the charge. So there won't be any shifting of the isomeric shift, right? So if the ligands are not at all participating in your shifting of the electrons, so it would have been constant. Like as soon as the electron oxidation state has changed, ligand should not participate, and therefore we will just compare the oxidation states of the metals. But since the CPs are there, that these kind of ligands are there, they start when they see that okay, oxidation state is being lost from the metal center. Now they will start putting up more electrons from their they would be kind of overlapping, and electrons will come from the ligands to the metal. Therefore, it will still maintain its iron in +2. Even though we can see it is an iron in +3, but if you see the spectrum, it will come exactly at the same isomeric shift because the penetration of the s electrons, it more or less same as in case of iron to an iron +3. So is this point clear? Like in this case of redox non-innocent ligands, it will not have any change in isomeric shift value. So is this clear?
Clear, ma'am.
So here we can't just say, we can't just see the iron in +3 and just jump to the conclusion that, okay, the delta value would be 2 negative. Here we have to analyze the factor that ligands are also participating. But when we talk about the quadruple splitting, that is 0.1, why is it happening? So iron in +3, it is actually having S equals to half system, right? So that would be D5 low spin. So it's only having if I'll consider this kind of thing. So it is having only one paired unpaired electron. So S equals to half system is there. So what really happens in this particular case, it appears the Cramer's doublet. So what is this Cramer's doublet that splits into two particular states? What happens here? Spin motion is there, but along with that, orbital motion will also happen. So as a combination that you might have heard about the magnetic moment. So S plus L, only the spin value, only the angular orbital value. So when both spin and orbital motion, they start coupled together, there would be some kind of changes and therefore Cramer's doublet will appear. And because of that, one part of that would be giving EFG in one direction, other part would be EFG in opposite direction. So the net EFG becomes 0. Therefore, we don't see any splitting in case of ferrocenium. That's why here only one peak is coming. There is no splitting occurring. Okay. Any doubt?
No doubt, ma'am.
So the last part before we take the assignment questions. So we have mixed valence biferrocenes. So what it really means that if we have a system like this way, where it is bound with iron, And this is also bound with iron here. This is in +3. So these kind of systems where iron is in +2, iron is in +3. So this is called mixed valent. So one case could be we have iron 2, iron 3, one is ferrocene, one is ferrocenium. So they both remains localized. That means they are not interfering with each other. The population of iron 2 will be same and iron 3 will be same. That is the first case. Second case would be like they interchange, that this gives one electron to this one and it becomes iron +3 and this one becomes iron +2. So there is an interchange. That means delocalization happens because of the electron transfer. And the third case is if they have shared the electrons and ultimately they are just giving 2.5 oxidation state after the electron transfer is happening. Like both of them are having exactly same number of electron density. So these three cases will be analyzed by the MOSFET spectra. So in the MOSFET spectra, how do we see the, how do we get the results? If we have just one kind of spectra, so in this particular case, and then it starts having, I need to draw with different colors. So here, if I'm having, so as you can see, this case, when we have just identical, there is a splitting, but it is giving us one signature only. So this appears for RNN plus 2.5 because plus 2.5, because of its electric field gradient, there would be splitting happening, but not two peaks are coming. So this particular case is indistinguishable when both the ions are having just the same oxidation state. So both the ions are having same oxidation state. So they will give this kind of spectra where it is having certain kind of delta value and only splitting is happening between the two peaks. Whereas if you see the next case, and in these cases, it is like just crossing of the peaks. So here they becomes like more predominant as soon as we are decreasing the temperature. So here is 115 Kelvin, it is 250 Kelvin, it's 270 Kelvin, and it's 287 Kelvin. So as we are decreasing the temperature, we could see the two different states over here. And here we have, so this would be completely, so this would be completely blue over here. And the green ones would be here. So these are the case when, since we know that which one is going to be the iron 2 and which one is going to be the iron 3. So this is a class 2 where the delocalization is happening. So we could have 4 peaks. The splitting of both the peaks for iron 2 and iron 3 will occur. And therefore we could have a 4 peaks over there. But if there is a case when both irons are having just the plus 2 5.5 oxidation state, that will give you only 2 peaks. So that kind of signature comes from the MOSFET spectra. And therefore, from this mixed valence by ferrocenes, we get to know which one possibility is there. If both of them are localized, that time also we can get to know about the splitting of it, but it depends upon the temperature. But mostly in the case of case 2, where electron transfer is happening between the two metal center, the one which is plus 2 oxidation state, it will lose the electron and give the electron to the other metal and itself becomes +3. So there would be +2 and +3 over there. And if they shared an equal number of electrons, they would become 2.5. And from the spectra, we get to know as we lower down the temperature, at low temperature, we can identify iron 2 plus and iron 3 plus. That means 4 peaks would be there. And for iron 2.5, there would be only one signature. That means 2 peaks are there. So is this clear?
Clear, ma'am.
Okay, then we'll quickly take up these questions. I would recommend that please read and go back and watch this video because it's very difficult to finish off all these concepts in 2 hours of time. So if I would have gone in a rush, so please let me know. We can have this kind of discussion again in the extra live session that I'm going to take on 15th October after 14th October. I know that's Sunday, but on Sunday only before your exam start, we need to have an extra class where we will be discussing the some major topics like character table or something. And if there is any doubt in any question, that also we can have in that live session that will start from 5 to 7. The timing, please you remember, in because there we are having the sessions at 7 to 9. On Sunday, 15th October, we will be having class from 5 to 7 with the same. Okay, so now we'll quickly take up the questions. If you have understood today's lecture, you will be able to answer the questions. So the first question is straightforward because we took the first example of this one. Among iron F2, Cl2, Br2, I2, which one is having more isomeric shift? Whenever they are having more, they are not defining negative or positive, consider that to be as a positive one. So whenever they are asking which one is having more isomeric shift, that means they are talking about the positive ones only. So you need to identify and tell me the answer, which one. You have already tried this question, so this would be quite easy for you.
FeI2 is more isomeric shift, ma'am.
That's again the wrong answer. Now we just yes, we saw it, right? Because then F2 is making an ionic bond. Because of the ionic bond, it retains its d electrons. So when it is having d electrons into the iron only, so more d electrons, more shielding. More shielding means less s electron penetration, therefore less negative, or we call it as more positive. So when it is asking more isomeric shift, we are considering the more positive value. Iron F2 is the one which is having more positive value.
Yes, ma'am. FeF2 having more isomeric shift.
Yeah. So FeF2 is one which is having 1.4 value. So on ligand exchange, the second question says, on ligand exchange, we have iron H2 whole 6. When we exchange it, sorry, this is 6 ligands, 6 CN ligands. Find the right trend of quadrupole splitting. So we have already understood that ABC complexes, when we have iron aqua 2 plus, when we are giving the CN ligands, firstly, it will form H2O, CN whole 5, 3 negative, and then it forms iron CN whole 6, 4 negative. So you need to tell me which one is going to have the maximum quadrupole splitting and which one is the least one. So what is the right trend?
FeCN6 is the least quadrupole splitting, ma'am.
Yeah, it was not giving any splitting. It was just a singlet. So only B option and D option is having the CN6 as the minimum one. Right, this one and this one. Now identify which one is having the maximum. No, not this one. Oh, only this option, B option is the right one.
B option is right one, ma'am.
D or B? We have to find out which one is having quadruple splitting. If D is the right option, then you are saying that iron CN6 is having quadruple splitting. It was just a singlet, right? This was not having ligand contribution, lattice contribution, neither valence contribution. So it was having delta EQ is equals to 0. That means it was not at all having any quadruple splitting. So the right option is
D.
D or B?
B, ma'am.
Okay. So because we have also seen that in iron H2O, lattice contribution is there, valence is also there. In case of this one, it is making a low spin. So lattice is only there, valence was not there. So that's why the right answer is B. Find the point groups of staggered and eclipsed ferrocene. So what is the staggered one? Do you remember the point group?
Staggered, ma'am, eclipsed D5H, staggered D5D. That is the point.
Yeah, so this is right. I hope you have not just remembered it, you know how to find out the prime point group. That's why I'm not asking more. So now assign these. There are three isomeric shift values have been given. 0.53, we have just discussed this example, 0.50, 0.49. And these are the three ferrocene complexes. First one is A is FeCp2, B is FeCp, Cp star, and C is both of them as Cp star. So which one is having which value?
0.53 for A complex, 0.50 for B complex,
And this is 0.49.
0.49 for C complex.
Because of more electron density coming from the Cp star, to balance it out, iron loses its d electrons. Therefore, when it loses its d electron, the isomeric shift becomes more towards the positive side. Not more towards, yeah, it's more negative side. So now you assign the possible combination of isomeric shift and quadruple splitting. Similarly to ferrocene and ferrocenium, we just discussed that which this is first value like 0.53 is delta value, 2.39 is quadruple splitting, and these are the other options. Which one you feel is the right combination for ferrocene and which one is for the ferrocene? Think we saw that even if we are having the oxidation state of +2 and +3, still because of the redox nature of the Cp ligands, they do not let that total charge to go anywhere. So they balance out the charge. So is there any change in the isomeric shift for ferrocene and ferrocenium?
Ferrocene and ferrocenium. Isomeric shift is available, ma'am.
Isomeric shift is
available.
It is
for
available.
both.
It is fine. But is the value is same for both of them or it is different?
Different, ma'am.
Just see this one.
No, isomeric shift is same, ma'am. But del EQ is different.
Delta EQ is different. That I understood. But why isomeric shift is same for iron, ferrocene and ferrocenium? What actually happens here, I will repeat it one more time. So in ferrocene, we have iron in +2. But in case of ferrocenium, iron is in +3. If you go by the oxidation state. So iron +3 should be having more delta negative or they should be having different delta values. But what really happens, as soon as this iron goes in +3, Cp star or Cp ligands, they tend to give more electron density to balance out the charge. So ultimately, it will behave as iron 2 only. That's why their delta value does not change. Because they are redox non-innocent ligands. That's why they balance out the charge. They do not let the iron be deficient. That's why they give the electron density and they maintain the isomeric shift. So therefore, isomeric for both ferrocene and ferrocenium is constant. Only the delta EQ value is negligible for iron 3, as we saw that because of spin orbital coupling, the net EFG, that net electric field gradient is 0, and therefore we don't see any kind of split. So therefore, in this particular case, the option of this 0.53 and 2.3, it's for ferrocene, and 0.53 into and this 0.1, that is for ferrocene. Okay. Now try the last question. In case of the mixed valence biferrocene that we understood, how many peaks observed for class 2 and class 3, where class 2, where we have delocalization or electron transfer between two metal centers, and class 3, both of them are in +2 oxidation, +2.5 oxidation state. So how many peaks we saw? I'll show you the graph. Anyway, that would be the answer, but still. So here you saw that in case of iron 2 and iron 3, which is a class 2, we can have the peaks for iron 2 also, iron 3 also, right? So that is a case of class 2. So how many peaks? 1, 2, 3, and 4. Whereas in case when we are having 2.5 plus oxidation state, that means we cannot distinguish which one is what. So both irons are having same oxidation state. So they will only give you splitting of, like, one peak will split into two. So therefore only 2 peaks over there and 4 peaks for the class 2. So the answer for this question is class 2 is having 4 peaks and class 3 is having 2 peaks. So right now I still feel that you can go back and read this, and if there is any doubt, you can come back to me in next live session or in the extra live session to have more understanding of it. These are the all sorts of examples for iron case where we expect to have a certain kind of trend, but the trend comes in a different way. So we need to understand and comprehend the reason behind it. So as you saw, like, we were expecting some kind of trend for iron halides, but it came out to be different. Similarly, in case of the CP star where methyl is giving more electrons, that time also trend was different. And here also when iron 2 is there, iron 3 plus is there in ferrocenium, the trend was out of the expectation that it is giving same delta value. So that's why all sorts of examples of iron cases has been taken. So to give you a broad picture, like what kind of MOS, only based on the experimental theory, experimental observations, like how the spectra is looking, we come to the conclusion what kind of different metal states and different coordination, the spin complexes exist in the that particular scenario. So if all this is clear, or is there any doubt in this live session? Otherwise, we can end this.
Okay, ma'am, no doubt.
So I would suggest you just try and read this and watch this again, and we'll be covering having the last, according to the syllabus, the last live session would be next Saturday, but there would be an extra live session from 5 to 7. I'm again writing it on the first slide. Please remember the timing, because many students are joining in their own timings and they are not attending at 7. So this is for the 15th October. You will also get a notification from NPTEL team. 15th October, we are going to have 5 to 7. That's an extra class. There we will be having a discussion of the character tables and some other examples, which will help you for the exam. So with that, I would end up the session. Thank you for joining me.
Thank you.